This is a recording of a webinar presented by Dr. Bethany Bray on March 29, 2018. The recording consists of a 1-hour presentation followed by a 1-hour question and answer session.
All right. Hello, everybody. Welcome. Thank you, Erin, so much for that introduction. For those of you who maybe don't know me in person, hello. You can see my little video. I have kind of a colorful office there. But we're going to mostly, for the first hour, of course, focus on the lecture that I've prepared that's focused on latent transition analysis. For the second hour, we'll have a live question and answer session. As Erin said, if you have any questions throughout the presentation that you want me to talk about at the end, please type them in the chat box and he will feed them to me one at a time. So again, welcome. Thank you for joining us. We have quite a crowd, so happy to be talking about LTA. Let's get started. Take care of that. All right. So what are we going to cover today in the next hour? We're going to start off with a conceptual introduction, both to latent class analysis, very, very briefly to set the stage for latent transition analysis. And then we're going to really spend the bulk of the time walking through an in-depth example of LTA to give you a flavor of the kinds of questions that you can answer. Towards the end, if we have enough time, I'm going to very briefly talk about why you might want to add a grouping variable into a latent transition analysis, and then also predicting both membership in the latent classes that are changing over time and how to actually predict those transitions between the classes. So again, this particular webinar is really focused on that longitudinal extension of LCA. I realize some of you may be more or less familiar with LCA, so let's do a very brief introduction to latent class analysis, and then we'll spend most of the time on latent transition analysis. As I'm sure most of you know, the basic idea of latent class analysis, or otherwise known as LCA, is that individuals can be divided into subgroups or latent classes based on some unobservable construct of interest. Now, we have the idea, just like in factor analysis, that our true latent class membership is unknown due to measurement error, for example. But the classes are mutually exclusive and exhaustive. So what that means is that we're trying to ask participants in our study perhaps questions on a survey, and we're trying to uncover the subgroup to which they belong. And we know that they belong to one and only one, but we're not 100% sure which one, because we want to account again for that measurement error in their responses. Because we're interested fundamentally in this idea of measurement error, just as in factor analysis, we base the measurement of our latent construct on several categorical indicators. Okay, so in factor analysis, we're talking about a continuous underlying latent factor that is typically measured with continuous items. In this case, in LCA, we're talking about a categorical latent variable that's typically measured with categorical indicators. If you're interested, we can talk more about continuous indicators during the discussion. So as I said, LCA is fundamentally a measurement model, and we're concerned with the error that's associated in the measurement of those latent classes. Again, it's similar to factor analysis, but the latent variable is categorical rather than continuous. So let's see if we can take those very general ideas and make them a little bit more concrete by looking at a preliminary example. So before we jump really in depth, let's take a look at a very brief example focused on depression. So we're going to start off with an example of LCA just to get a flavor of this. So let's say that I asked participants 8 questions about how depressed they were feeling. So for example, I could ask them, in the past 2 weeks, did you feel like you could not shake the blues? Did you feel depressed? Did you feel lonely? Did you feel sad? Did you feel like people were unfriendly to you, or that you were disliked by people? Or did you feel like your life was a failure or your life was not worth living? So if I use those 8 questions to assess depression, there are 256 possible ways that people could respond to those questions. Now, if I'm a clinician, I might be interested in something like a sum score, and I might say something like, if you endorse 5 or more of these criteria, then I'm going to classify you as depressed, and if you answer fewer than 5, I'm going to classify you as not depressed. But in the case of latent class analysis, I might be more interested in the idea of, do characteristics of sadness and feeling disliked, do they co-occur together within individuals in particular ways? So for example, even if you don't get up to that clinical threshold, we might determine that you could participate in, say, a targeted intervention program where your depression is elevated in a particular way, and we want to target a particular kind of intervention program to you. So what does this look like? So if we go through the process of LCA, which you can either read about or you can watch some of our other videos about, in the depression example, let's say that we identify 5 latent classes. And maybe the 5 classes that we identify are no depression, sadness only, disliked only, sad and disliked together, and depressed. One of the questions that we might have is, what are the prevalence rates of all of these classes in the population? And so this particular example is coming from wave 1 and wave 2 of the AdHealth data. And you can see that about 41% of our population was expected to have no depression. Okay? In contrast, about 9% of them were expected to belong to the class that we would think of as depressed. Now, you might think, okay, well, I might expect these classes to come out, and that is true. So the sadness items are kind of hanging together, and this disliked items are kind of hanging together, and then they occur together, and then we get depressed. But one of the interesting things that's happening in this example is the sadness items are producing one class called sadness, about 18%, and the disliked items are producing another class, here we call them disliked, at about 17%. But what we don't know is which set or which group of individuals is more likely to escalate over time and transition perhaps into that depressed class, or maybe less seriously transition into experiencing those kinds of symptoms together. So if we're still talking about LCA, you might be curious how we come up with the labels for these classes. And so as you know, in the previous slide, there are 2 sets of parameters. The first one are those prevalence rates that I just talked about, and that's how big the classes are in the population. But the measurement parameters are the item response probabilities in latent class analysis, and they're conceptually similar to factor loadings, and they're how we give the classes names. So what you're looking at on the screen right now is what we call an item response probability matrix. And what you're seeing is the probability of people responding yes, they experience that indicator conditional on their latent class membership. And so what we do is, just like looking at a pattern of factor loadings in factor analysis, we look at the patterns of item response probabilities and we try to label the classes. So if you look in the first column, class 1, what you see is that participants who were in class 1 had very low probabilities of responding yes to any of those indicators. So for example, they had a 3% chance of responding, yes, I could not shake the blues in the past 2 weeks. Because the item response probabilities are low across all of the items, that's how we come up with the label of non-depressed. They're not very likely to illustrate or to endorse any of those questions or criteria. As we move across the table, you see different patterns of endorsement of those items. So class 2, what you see is elevated probabilities of responding yes to couldn't shake the blues, felt depressed, felt lonely, felt sad. Sorry, the 0.17 shouldn't be bold. So the probabilities of responding to the other items focused on feeling disliked and feeling like life was a failure are low. So we labeled that class sad. Class 3 was named in a similar way. The probabilities for feeling disliked were elevated. class 4, you can see that the items for sadness and disliked were elevated. And then class 5, we labeled depressed. And what is unique about that class is that they're really bringing in that dimension of feeling like life was a failure. So they're really endorsing all of these criteria. Now, if you were a clinician, for example, perhaps, again, you're just interested in that clinical cutoff of depressed or not depressed. Depending on where you set that cutoff, perhaps people who belong to class 4 and class 5 would be likely to be diagnosed as depressed, and people who belong to classes 1, 2, and 3 might be classified as not depressed. But as an intervention scientist, I might be particularly interested in the people who are in class 2 and class 3 because perhaps they're subclinical and I want to prevent them from escalating in their depression. But also they might require different intervention programs. People who are feeling sad might say require an intervention program to get them more engaged in a wide variety of activities, where people who are feeling disliked might require an intervention, say, focused on cognitive reframing or something like that. So when we're interested in applying LCA to a data set, we're primarily interested in these two sets of probabilities. The latent class prevalences, so again, those are the sizes. So for example, the probability of membership in the depressed class. The other set, again, are the item response probabilities. So for example, the probability of reporting that you felt lonely given membership in the depressed latent class. If we move on to latent transition analysis, the key feature is that LTA is a longitudinal extension of LCA. So it requires at least 2 waves of data. And the idea is that you want to model development as movement through a set of discrete categories or stages. So in this depression example, I'm particularly interested in, say, the proportion of people who move from the SAD only class to the SAD and disliked class. Now again, LTA is a measurement model, just like LCA. It comes from a measurement tradition. And so we know that there is error associated with the measurement of the classes, which means there's also error associated with understanding the transitions in class membership. In this model, because it is based on stage sequential change, different individuals may take different paths. So for example, an individual who starts in the non-depressed class, some of those people might move to sadness before they move to sad and disliked and depressed. Other people might move to disliked first before moving to sadness and disliked and then on to depressed. So there's heterogeneity in that movement, and that heterogeneity is unobserved or latent. So again, as a summary, LTA provides a way to estimate and test models of stage sequential development. In LCA, those classes are static, and in LTA, those classes are dynamic, and people are allowed to move between them over time. Sometimes, if you've been reading more historic literature, often those dynamic latent classes are referred to as latent statuses. So latent statuses, latent classes, they mean the same thing. To keep things consistent in the context of this discussion, I'm just going to refer to everything as latent classes, but we are talking about dynamic latent class membership. So in addition to those latent class prevalences and the item response probabilities that you're interested in with LCA, in LTA, we can also estimate the incidences of transitions between those latent classes or latent statuses over time, again, adjusted for measurement error. So for those of us who are a bit more graphically minded, I'm going to show you 2 different graphs that, 2 different figures that represent kind of the same ideas. So what this is here is kind of what I just described about people moving from non-depressed. Some of them go to sad, some of them go to disliked. So for example, latent status 1 here might be no depression. Some folks over time might move to the sadness only before moving on to the sad and disliked, whereas another group might follow the bottom pathway by moving from non-depressed to disliked only, and then up to sad and disliked. Sorry about the clicking. My keyboard is a little loud, so I'll try to move to the mouse. If it's distracting, please send us a message and I'll try to remember. For those of us who are a bit more familiar with, say, structural equation modeling or graphical depictions of models in M+ or factor analysis or anything like that, here's another way to graphically depict a latent transition model. So as with all of these figures, latent variables are in circles and observed variables or manifest variables are in the boxes. And so what we see here is in the latent transition model, we're interested in expanding the depression. We're interested in looking at development and depression over time. So we have depression classes at both time 1 and time 2. At time 1 and time 2, they're also assessed by that same set of 8 items, focused on sadness, disliked, and life was not a failure. And then the arrow going from time 1 to time 2, that's really that transition piece that we're interested in. So where you, what is the probability of being in a particular class at time 2, conditional on where you are at time 1. And so that is represented by that arrow between the 2 latent variables. So again, hopefully you're starting to see the theme: transitions, longitudinal data. In addition to those prevalences and measurement parameters, we're now interested in transition probabilities. In our depression example, we might be interested in the probability of membership in the depressed class at time 2, conditional on membership in the sad and disliked class at time 1. So again, I am half a methodologist, half an intervention scientist. And so I might be interested in those rates of transitions in order to be able to implement a prevention program at a particular time point. So we've already taken a look at the sizes of the classes, and we've taken a look at the measurement structure of the classes. So what is that piece that LTA is adding? Again, that is the transitions, and those are typically expressed in a transition matrix. And we're going to unpack all of this in more detail. But a standard transition matrix is set up like the one that's on the screen. So the time 1 latent classes are in the far left-hand column down the rows, ROWs, and time 2 is the columns. And so the way that you read a transition matrix like this is, given that I belong to a particular class at time 1, what is the probability that I belong to a particular class at time 2? So here, for example, among individuals who are not depressed at time 1, 77% of them also reported being non-depressed at time 2. In contrast, 46% of the people who reported feeling disliked at time 1 were also reported feeling disliked at time 2. Let's see. For people who moved, perhaps we could look at, so in the sadness row, among people who reported being sad only at time 1, about 7% of them reported feeling disliked at time 2, and another 7% of them reported feeling both sad and disliked at time 2. So this matrix is what we call row conditional. That means that the probabilities sum to 1 across each row. So again, it's given where you are at time 1, what is the probability that you're in a particular class at time 2? As a summary, LTA provides a way of fitting models with these characteristics, all of which we've talked about. So change is discrete, that's that stage sequential piece. Data are longitudinal, that means you need to have data from at least 2 or more times. Measurement error is a prominent feature that you're interested in. Again, latent transition analysis comes out of a measurement framework, just like factor analysis. And then we're also interested in heterogeneity and development. Again, that's people making different transitions across time. So let's see if we can unpack these ideas in a bit more detail. The depression example is kind of a 30,000-foot overview of the dimensions of the model that we're most interested in. But let's take a deeper dive into this model of sexual risk behavior over time. So the goal in this model, the goal in this paper was to model change over time in dating and sexual risk behavior among adolescents and young adults. And this example is based on a paper by Lanza and Collins in 2008 in Developmental Psychology, if you're interested in unpacking this and learning more about how to fit these models in SAS. So the goal of this paper was to fit a developmental model of dating and sexual risk behavior across 3 times. And we had several research questions that we were trying to address that we felt were best addressed using LTA. So we're going to look at the latent structure of dating and sexual risk behavior, and we're going to unpack that first. So we'll look at how many latent statuses there were, what are their interpretations. Then we'll look at the sizes of the latent statuses or latent classes once we understand what they are. And then we're going to look to see how people transition across those 3 times. So we're going to look at transitions from time 1 to time 2, and then transitions from time 2 to time 3. These data were from the National Longitudinal Survey of Youth 1997, or the NLSY 97. In this particular case, we really narrowed our sample to focus on people who are very similarly aged. So we were just looking at US high school students age 17 or 18 at time 1 and looking at those transitions kind of post high school. There were just over 2,900 of them, slightly less than half of them were female. And if you're interested in these data, we happen to use the waves from 98, 99, and 2000. As a side note, married participants were not included. We thought that if you were married at ages 17 or 18, probably your sexual risk-taking looked a bit different from the rest of the population. In this example, we used 4 indicators of dating and sexual risk behavior. And I like this example because people often ask me in LCA or in LTA, can I only use binary indicators? And the answer is no, you can use indicators with more categories than just 2. And so this example is going to show you what these models look like when you have more than 2 classes, when you use indicators with more than 2 levels, and when you use at least 4 indicators. So here what we have are indicators for dating partners. So that's the number of dating partners that you've had in the past year, whether or not you've had sex in the past year, what is the number of sexual partners you've had in the past year, and then this exposure to a sexually transmitted infection or STI. And so that is at least 1 instance of intercourse without a condom in the past year. So in this example, we were particularly interested in setting very severe cutoffs that would indicate any level of increased risk. So for dating partners, we looked at 0, 1, and then 2 or more. For past sex, it was either yes or no. Number of sexual partners, again, that had a very strict cutoff to represent risk. So it was 0, 1, and then 2 or more. And then again, the condom exposure was yes or no, you were potentially exposed to an STI at all by even 1 instance of unprotected sex. So we're going to use those 4 indicators and latent transition analysis to identify and describe underlying classes of dating and sexual risk. And once we identify and understand what those classes are, then we're going to use LTA to examine transitions between those underlying classes across 2 years. So there's, of course, behind the scenes, an entire model selection process. This is just an intro to LTA, so we're not going to get into the details of that. If you have questions, I can talk more specifically about that during the discussion hour. But assuming that we selected the correct model, in this case, we were looking at 5 classes or 5 latent statuses. So what you see on the left-hand side, of course, are the 4 indicators we were talking about. Across the top are the 5 statuses. And the first thing that we need to do is we need to understand this measurement model to understand what the classes are. So in bold are the entries that we felt were elevated and helped us understand the interpretation of that class. So status 1, you can see that they had elevated probabilities of reporting 0 dating partners, no past year sex, no past year sex partners, and no exposure to STI. In latent status 2, what you see is that they had elevated probabilities of having 2 or more dating partners, but no past year sex, no partners, and then of course no exposure. Status 3, 4, and 5 are covering the people who had past year sex. And so what you see is in status 3, they probably had 1 dating partner, but many of them had 2 or more. They did have sex in the past year, but they only had 1 sex partner, and they may or may not have used a condom 100% of the time, which translated into that exposure to STI. That's that 40 and 60% there in the bottom cell for status 3. And statuses 4 and 5, or classes 4 and 5, they were very similar. They had 2 or more dating partners. They definitely had sex in the past year, and they had 2 or more sex partners. But in status 4, they used a condom 100% of the time, and in status 5, they did not use a condom 100% of the time. And so if you're not comfortable looking at these kinds of charts, you can let your eyes go fuzzy a little bit. And what you see here are just those elevated probabilities. And you can see how we turned those into labels for our classes. So class 1, we labeled non-daters. Class 2, we labeled daters. Class 3, we labeled monogamous individuals. Again, they may or may not have used a condom 100% of the time. And then classes 4 and 5, we contrasted to each other in that they both were multi-partner, but one was safe and one was exposed. And again, that just has to do with using condoms 100% of the time. Once we understand the structure and interpretation of the classes, then we can move on to looking at the prevalence of those classes. And so again, we had 3 times in this particular example, time 1, time 2, and time 3. And what you see here is that we can get the sizes of the classes at each of those 3 times. So we see that in time 1, again, that's when they were 17 or 18, about 19% of the individuals were non-daters, 29% were daters, 12% monogamous, 23% multi-partner safe, and 18% multi-partner exposed. The spacing of the data collection was approximately 1 year apart. And so what you can see is approximately 1 year later, we have the rates for membership in each of those classes. And then again at time 3, probably unsurprisingly, normatively during this developmental period, the rates of non-dating are decreasing a bit, as is dating only. People start engaging in more sex, and so you see that the monogamous rates are going up. Multi-partner safe is staying about the same, maybe decreasing just a tiny bit, and then multi-partner exposed is increasing a bit. So again, these are the prevalence rates at each of these 3 times. So we don't know, although we know the sizes of the classes during each of those years, we don't know if it's the same individuals in those classes. So people could be moving in and out across time, and that's what we're particularly interested in this example. So the unique feature of LTA as compared to LCA, of course, is this transition matrix. And what you're looking at now is that new unique piece that we want to try to unpack. This is a little bit larger transition matrix than what we were looking at before. Again, down the columns on the left-hand side, that's, down the rows on the left-hand side, that is the time 1 latent classes, and the columns across the top, those are the time 2 latent classes. The blue entries are the transitions from time 1 to time 2, and the green entries are the transitions from time 2 to time 3. So this is a lot of numbers. How would you go about unpacking this for paper that you're writing? Well, one way that I like to do this is I like to start by understanding across the entire transition matrix how many people are actually transitioning in their class membership. So you might start by looking at what I refer to as the stability parameters, and those are the probabilities down the diagonal. Here they're highlighted in green, light green. And so what we see is that there is, a relatively high amount of stability, but people are transitioning over time. So let's see. So let's start with the non-daters up in the upper left-hand corner. What we see is that among people who report being non-daters at time 1, about 61% of them report being non-daters also at time 2. In contrast, if we look at monogamous individuals in that third row, what we see is among monogamous individuals at time 1, about 68% of them also report being monogamous at time 2. And then if we look down in the lower right-hand corner, perhaps somewhat troubling if we're public health scientists, is that the stability parameters for that multi-partner exposed, the people who are at highest risk in this particular example, are really quite stable. They're the most stable. 81% of them also report being multi-partner exposed at time 2. And then if you're multi-partner exposed at time 2, 72% report multi-partner exposed at time 3. So once I start to get a flavor for how much movement is going on, generally speaking, again, that's the stability parameters, then I might want to focus in on specific parts of the table that correspond to either particular research questions of interest or particular hypotheses that you want to test. Again, the motivation for this example was really focused on this public health problem of who is transitioning to have the most risky sexual behavior. So I might be interested in people who transition into the multi-partner exposed class. And so what you can see is that highlighted in yellow, those are the conditional probabilities of belonging to a particular class at time 1 and transitioning into multi-partner exposed at the subsequent time. And so what you can see is that the monogamous individuals are, although monogamous individuals are still most likely to report being monogamous at the follow-up time, if they transition, they are most likely to transition to multi-partner exposed, and across all of the classes, they're the all of the classes that are not multi-partner exposed, they're also most likely to make that transition. Another thing that I might be interested in is, do people in the multi-partner exposed latent class transition back to being monogamous? And so you can see about 15% of them do transition back to being monogamous from multi-partner exposed. So what we're seeing here in my interpretation is that there's quite a bit of movement between the monogamous latent status and the multi-partner exposed latent status. Again, as an intervention scientist, so the red box should be around the 0-0 entries. So if I'm interested in a public health question, one public health question that I might be interested in is whether or not people do have any hope of starting to use a condom 100% of the time after they've reported not doing that behavior. And what we can see is that from time 1 to time 2, and then again from time 2 to time 3, 0% of the people report moving from multi-partner exposed to multi-partner safe. So we have a ways to go in that dimension. These slides will be made available to you when this talk is archived, and so the next couple of slides I'm just going to go through quickly. It's really just for you to have when you take them home. It's just a summary of findings. It says what I just said. So increasing membership in the monogamous and multi-partner exposed latent statuses over time. And then you can get that from those prevalence rates. But then the second bullet of membership in the multi-partner exposed latent status is the most stable. That has to do with that transition probability matrix. Again, members of the monogamous latent status were most likely to transition to that very high risk latent status of multi-partner exposed. And unfortunately, no one in the multi-partner exposed latent status was expected to transition into a safer status of multi-partner safe. All right, let's take a little breather, sip of my tea. I know that most of you probably on this call are not focused on high-risk sexual behavior in your own work. So I just wanted to do a bit of a survey of other examples of LTA in the literature to try to help you start thinking about creative ways that you could apply this methodological tool in your own work. So LTA has been applied a lot in substance use literature. So LTA kind of grew out of substance use initiation work and substance use escalation. So there's a lot of applications to things like the gateway hypothesis, for example, onset of substance use. And then there's been work in recent years that is particularly focused on transitions in drinking behavior specifically. So for example, transitions in first-year college student drinking behaviors. This is the Cleveland et al. 2012 paper. And they identified classes like non-drinkers, weekend non-binge drinkers, weekend bingers, and then heavy drinkers. They also happen to look at intervention effects on the transition. So if you're an intervention scientist, you might want to look at that paper. And in parentheses, you can see, non-drinkers, probably unsurprisingly, that's decreasing. Heavy drinkers is increasing across this first year experience. But substance use and risky sex are not the only places that have applied LTA. So there are examples of both latent class analysis and latent transition analysis in eating disorders. So here is an example about eating disorder phenotypes in a clinical sample. And so they're focusing on different strategies of controlling your weight or controlling your eating behavior. So severe binging, moderate binging, restricted eating, binging and purging, etc. Another example in the substance use realm, so LTA has been applied a lot in smoking behavior. This example I think is particularly interesting because it focuses specifically on the behavior change theory, stages of change. So pre-contemplation, contemplation, preparation. So this is for smoking acquisition and cessation. This particular study is among adolescents. If you're more on the contextual side of things, or if you're more on the sociology side of things, or you're just interested in maybe risk at multiple levels, there has been work looking at more kind of structural related characteristics and trying to identify people who are experiencing different contexts. Also, different types of socioeconomic status indicators, for example, and how those are changing over time. This particular example is on social information processing of aggression, combined with community violence, aggression, and then also behavior regulation. For those of you who are interested in risky sex, or maybe even more specifically HIV, LTA has also been applied in those areas. This is an interesting example looking at transition in HIV risk behaviors, particularly among injection drug users. And so it's really focused on their needle sharing behaviors. Again, if you're more interested in physical activity, exercise, or obesity, LTA has been applied to transitions in classes of meeting or not meeting Healthy People 2010 recommendations, and also the effects of an intervention to increase people's physical activity and high quality eating behaviors. So the intervention significantly increased membership over time in the healthier classes, and so promoted individuals transitioning to better classes over time. So really all of that is to say that no matter what you study, LTA might be relevant to you and could potentially help you address research questions about longitudinal development over time. I'm going to very, very briefly talk a little bit more about transition parameters, and I'm focusing on the transition parameters here, again, because this is really the unique piece of why you would choose LTA over LCA. So again, the transition parameters are arranged in what we call a transition probability matrix. You don't need to worry too much about this notation, but remember that time 1 is on the rows on the left-hand side, and time 2 is on the columns. And again, they're row conditional, so they sum to 1 across the classes. So if you have particular developmental hypotheses, because we can explicitly express these transition parameters, we can test straightforward hypotheses about different types of development. So here's one example. Perhaps you're interested in whether or not people transition backwards. So maybe your classes represent increasing risk over time or something like that, and you want to test a model of what we might think of as no backsliding. Well, if there is no backsliding, what you would have is a transition matrix that would look like this. And so people are allowed to move forward, but the probabilities of moving backwards in that lower triangle of the transition matrix would all be 0. And so the question is, does your transition matrix that you see in your data, does it look like this hypothesized transition matrix if indeed no backsliding were true? And so you can compare the transition matrix that you have in your own data to the transition matrix that you would expect based on your developmental theory, and you can see whether or not your data support that theory. Another example would be maybe you want to test a model of no change over time. People just remain in their latent classes over time. And so that would have zeros on both the lower triangle because people cannot move backwards, and then also on the upper triangle because people cannot move forwards. So again, you would compare your observed transition matrix to the one that's hypothesized by, the one that corresponds to the hypothesis of no change. So once you determine that LTA could help you address some of your research questions of interest, there's a whole world of more complicated questions that you might want to ask. So for those of you who are more experienced with structural equation modeling, for example, you might be very familiar with why you want to fit a multiple groups SEM, right? You might want to look at, for example, gender differences in the factor structure and then how the factors are related to each other. You can also ask similar questions in LTA. So we're going to talk really briefly for the next 15 minutes about the questions that you can address using grouping variables and then also covariates, just to give you a flavor of the broad scope of questions that you can ask with these types of models. So we're going to continue to delve into that dating and sexual risk behavior example. And so once we identified the classes and interpreted them, and then we looked at how people were changing across time, we had additional goals of that study. So one additional goal was to examine gender differences in dating and sexual risk behavior. So we might think that differences in dating and sexual risk behavior might stem from two primary sources. The first one is this idea of measurement and variance. So is the structure of the latent classes the same for men and women? That question is the same as, do the items map onto the latent construct in the same ways for males and females, for example? We need to establish measurement and variance so that we can directly compare things like the sizes of the classes and transitions between the classes across levels of that grouping variable. So the first thing that you usually start with in LTA is looking at that measurement and variance across groups or even across times. Once we establish measurement and variance, then we might want to include a grouping variable to divide the sample into groups for comparison purposes. So in the context of this dating and sexual behavior example, we might be interested in how does the probability of membership in the monogamous latent class differ in, say, the experimental and control groups if I have an intervention? Or how does the probability of transitioning to that high risk status of multi-partner exposed differ between males and females? Are males or females more likely to make that transition? So what we did in this study was we put in gender as the grouping variable. In this case, the question was actually asked more based on biological sex. So we'll talk about males and females here. And what we see is that when we put in sex as a grouping variable, what we get are the prevalence rates of the 5 classes for males and then also for females. And so this is just at time 1. What we see is at time 1, about 17% of the males are non-daters, about 28% of them are daters, and so on. In contrast, for females, about 20% of them are non-daters, about 30% of them are daters, and so on. So what we see here is that for non-daters, daters, and multi-partner exposed, the prevalence rates are about equivalent. And what we're seeing is that males tend to be more likely to be in the multi-partner safe, whereas females tend to be, are more likely to be in the monogamous latent class. So if you're interested in questions like this, you could think of any number of grouping variables. So in this example, we might be interested in things like whether or not people are living below the poverty threshold. Pubertal status might be particularly interesting if our sample was a little bit younger, or even at this age too, about onset for sex. So whether you're early versus on time versus late in terms of your pubertal status. Or if I was a public health scientist interested in implementing an intervention for, say, condom use, we could have treatment group membership as that grouping variable. So you can think broadly about the kinds of grouping variables that you might want to put in the model. Just as with any other kind of model, structural equation modeling or whatever, grouping variables have to be categorical in nature. And just for take-home purposes, you can look at them later. I have some additional example research questions. So this one is, are children in households with low income more likely to be engaging in risky sexual behavior at time 1? So that's a question about that baseline prevalence. But then are females with early pubertal timing more likely to transition to risky sexual behavior than their on-time or late pubertal timing counterparts? So that's a question about the transitions. So when you put in grouping variables into an LTA, there are at least 3 pieces of the model that you might be interested in. The measurement invariance has to do with whether or not the measurement structure is the same. Differences in the prevalence rates, that has to do with those single time prevalence rate differences. And then you could also be interested in differences in the actual transition rates across time. But of course, everything in life is not categorical. And so what do we do about predicting membership in latent classes and transitions from covariates, or if you call them predictors, or continuous variables? Well, we can, of course, add, I'll call them covariates here, we can add covariates to the latent transition model to predict both initial status and transitions over time. And so in this example, we used different types of substance use to predict membership in those dating and sexual risk-taking classes, and then also to predict changes in class membership over time. The basis for these types of models, probably unsurprisingly, is regression. So just like in any other regression model, you can have multiple covariates. You can have all different kinds of covariates. Some of them can be categorical, some can be continuous, they could be count variables. So you can have 1 or more predictors of time 1 latent status membership, and then you can also have 1 or more predictors of those transitions over time. Because we're in the categorical world, just as a reminder, what we're really talking about then are things like baseline category multinomial logistic regression. Okay, so baseline category multinomial logistic regression is the default for predicting time 1 latent statuses and transitions over time. So because it's baseline category, you have to specify a reference group. In our case, we have 5 latent classes, and we pick one of them as our reference group. In this case, let's just take non-daters. And so what you got are 4 odds ratios representing the effect of a covariate on membership in any of the 4 target latent classes compared to that reference class of non-daters. And so what you can see here is we have daters compared to non-daters, monogamous compared to non-daters, multi-partner safe compared to non-daters, and then of course multi-partner exposed compared to non-daters. In this example, we looked at the effects of cigarette use, drunkenness, and marijuana on membership in those classes. And in this case, just to keep it straightforward, we're going to look at non-daters as the reference class. So the question is, if you report using, for example, cigarettes in the past year, are you more likely to belong to certain latent classes compared to others? The answer, unsurprisingly, is yes. Cigarette use, drunkenness, and marijuana use are all significantly related to membership in the latent classes. So this, you could think of this as an overall test or perhaps an omnibus test. And so you can get that overall test of, is your predictor related to latent class membership? But probably more interestingly, you want to know how those predictors are related to your latent class membership. If you like figures better than tables, you could easily present these results in a bar chart or a line graph, however you like to do it. I wanted to show you the actual values here. And so what you're seeing are the effects. These are odds ratios in this case, the effects of cigarette use, drunkenness, and marijuana use on membership in each of the 4 classes relative to non-daters. So let's try to just interpret one of these. Let's interpret the largest one, the largest effect size. So that would be for marijuana use. And so the way that we would interpret this is that adolescents who report marijuana use are 10.5 times more likely to be in the multi-partner exposed latent status at time 1 relative to the non-daters latent status than adolescents who did not report marijuana use or who reported no use. So another way to say that is that the risk of membership in the multi-partner exposed status relative to the non-dater status is 10.5 times greater for those who used marijuana. So again, that's the effect of a covariate on membership in one class compared to another at baseline, so at a single time. Of course, we're talking about longitudinal models, so perhaps the more interesting part is, do the substance use behaviors predict transitions into and out of classes over time? This example had a lot of sparseness, so we're not going to go into why everything's shaded in yellow and orange. If you want to know that, you can look to the paper. But let's take a look at the the effect of drunkenness, the effect of drunkenness on transitions out of the non-dating status. So the way that this is interpreted is that if you report marijuana use at time 1, so among non-daters at time 1 who report marijuana use, they're 3.6 times more likely to transition to the multi-partner exposed latent status compared to the non-daters latent status at time 2. Okay, and you can see the greatest effects. And I'm sorry, I'm saying marijuana use. I mean to say drunkenness. Right now we're looking at the effect of drunkenness. So non-daters who report drunkenness are 3.6 times more likely to make that transition into the very high risk latent status compared to staying non-daters. So again, I summarized the conclusions about substance use. So if you take these home and you absorb them, what I want you to get is the kinds of effects that we might be interested in these models. And so, bullet point 1 is about drunkenness and marijuana use predicting membership in one class compared to another. And then the second bullet is about drunkenness being a stronger predictor of transitioning to a different status compared to remaining in the same status. In this example, you might be interested in any number of covariates: temperament, academic achievement, age, if you have a wider age range, income to needs, if you're interested more in socioeconomic status. So again, there's really no limit other than sample size and things like that in terms of what you can put into model as a predictor. If you can put it in as a predictor in a regular regression model, you can put it in most likely into one of these models. Some additional research questions. Does child temperament predict dating and sexual risk behavior statuses at time 1? Or what is the increase in odds of membership in the high risk status relative to a low risk status corresponding to a 1-unit change in academic achievement? So academic achievement could be continuous. The interpretation is the same. It's all about 1-unit increase. Another example would be how does age relate to the probability of transitioning from one status to another? So I think we're winding up my 1 hour of everything that I wanted to tell you, kind of to kick off a discussion about LTA. I hope this was helpful, and I'm very pleased to stick around for the next hour and answer any questions that you guys might have. And I think we're going to turn the slides off so that you can see me. But if you want to refer to anything in the slides, I will have them. So please feel free. So let me stop the share. So I am going to use a hard candy. If you have trouble understanding my responses, please let me know. But this will prevent any coughing for the next hour. So excellent. Hopefully this was helpful. What do you guys want to know?
All right, so keep the questions coming in via the chat function or via the Q&A, and I will ask them to Bethany live. So the first question that came in was, what does an item response of 1.00 mean?
Yes. So, so that would be an item response probability on the boundary. And what that means is that given that you were a member of that class, you have 100% chance of providing that response. So for example, I can't quite remember if we had some boundary values in the dating and sexual risk taking that were 0. So given that you belonged to the non-daters latent class, you had a 0% chance of responding, yes, I had sex in the past year, for example. So those boundary values are important. Some people don't like them, but the idea is that the item response probabilities summarize the link between your latent variable and your observed variable. So just like in a standardized factor analysis, the strongest association between an indicator and the factor is -1 or +1. In latent class analysis with binary variables, well, actually with any kind of variable, item response probability of 0 or 1 is that perfect association between your latent class membership and your item response probability. So you're actually looking high quality membership. High quality membership. No, I just said it again. Sorry. High quality measurement is indicated by item response probabilities that are close to those boundary values.
All right. Several questions about sample size. So we'll bump that one up the list a little higher because Yeah, so that's a great question. You know, sort of historically, in all the years that I've been working in these kinds of models, you know, we used to say that you needed, you know, more than 300 people. Okay, that was really just kind of based on our sort of life experience. The answer to that is there's not a straightforward answer, just like there's no real straightforward answer in structural equation modeling. With latent class models, there have been a handful of papers that have looked at the sizes that you need to uncover particular latent classes. And basically, the fewer people that you have in your sample, the fewer classes you're going to identify because you don't have the power to detect small classes in the population. When you have repeated measures over time, like you do in LTA, you know, the power is increased because you have more information on those people, assuming your attrition rate is not really high. So it's a bit there. To my knowledge, there have been no studies looking at sample size specifically for LTA, but you can get a sense
of how well this is going to work by looking at the strength of your measurement model at a given time. And so the higher quality measurement that you have, the fewer people that you'll need to get a high quality model. And the reason for that is just like in factor analysis, the better the measurement, the more power you have to detect those classes. It's also a bit of an empirical question because these models, unless you're Bayesian, are fit using maximum likelihood. And so you have to be able to reliably identify the global maximum likelihood solution. And your ability to do that is harder the fewer people you have in your sample. So LTA, just like LCA, is a large sample size technique. You know, a couple thousand people, like in a nationally representative sample or an intervention study or something like that, that should, in my experience, be sufficient to run these kind of models. If you get down into the hundreds, then it's a little bit more of an empirical question of how many classes can you actually identify, and is your model, are you reliably identifying the maximum likelihood solution? I mean, I've seen models in the literature, LCA models in the literature with as few as like, you know, 150 people. I've even seen one that has 75 people in it. So I know that this answer is not totally satisfying, but I will give you the answer that I used in graduate school, which is you should, about 300 would be a good place to start. I will mention the two papers you might want to look at in the context of LCA for power calculations are a paper from the Methodology Center. The first author is Ziak, and the paper is Ziak et al. It's spelled D-Z-I-A-K. It's in, I believe, Structural Equation Modeling Journal. And then the other paper that people refer to quite a bit, although it's a little bit different, is the Nyland et al. Paper, which I think is from maybe 2007. The Ziak paper looks specifically at the bootstrap likelihood ratio test along with other fit criteria. The Nyland paper also looks at the bootstrap likelihood ratio test along with the Low-Mendel-Rubin test and other criteria too.
Thank you. Are there thresholds for the item response probabilities? For example, does greater than 0.60 mean you, quote, belong to the depressed class?
That's a good question. So let's think about item response probabilities in two ways. The first way is from a pure measurement perspective, okay? And let's say that you have binary items. Well, the probability that represents random responding, you could think of as being 0.5, right? So if conditional on the class, I have an item response probability of 0.5, what that means is if I belong to that class, I have a 50% chance of answering no and a 50% chance of answering yes. You might think that that doesn't provide a whole lot of information because it's kind of random. But there's another dimension that you have to think about, which is the overall prevalence of endorsement of that item in the sample. So let's think about substance use, right? Alcohol use, probably super prevalent depending on the sample that you have. Cocaine use, maybe not so prevalent. So let's say in your sample, the prevalence of cocaine use is, say, 1%. And let's say that one of the classes that you identified has an item response probability of 35% yes cocaine use. That actually provides you quite a bit of information about cocaine use, because even though it's not even above 0.5 and it's a binary item, you still know that the probability of reporting cocaine use among the people in that class is much, 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 much higher than the overall sample or the overall population. So the interpretation of item response probabilities, you use two basic principles. Well, yeah, two or three. The first one we often call homogeneity, which is within a latent class, how close are the item response probabilities to 0 and 1. And then latent class separation has to do with how uniquely how unique your classes are in their interpretation. And using those two principles, they're like simple structure and saturation and factor analysis to try to get a sense of the quality of your measurement model. But then when you look at those individual item response probabilities, you need to balance these ideas of kind of high quality measurement with how prevalent they are in the population, because random responding would be across all of the classes. If every single class reported 1% of cocaine use, that's not really that informative, because that's the same as your overall population. So you're comparing classes to each other, you're comparing item response probabilities to their boundary values, and then you're also comparing item response probabilities to that overall percentage. So it's a lot of things to balance in the interpretation.
We have a great set of really good questions. I don't know that we're going to have time to get to them all, but we will go through them as best we can.
Sure.
So in the sexual risk example, considering generality, can I say the proportion in the sample can represent the proportion in the population?
Yeah, so I kind of probably bounced back and forth about how I was talking about them. So latent class analysis, latent transition analysis, just like any other statistical model, you're trying to use your sample to infer something about the population, right? And so our sample statistics are used as population parameter estimates. And so I think there's one slide that said something like, we expect 19% of the population to be in this class. And so that proportion of 19% for the prevalence for that class, that is an estimate for the population. So you're expecting 19% of your population to fall into that class. Now, as with any other statistical technique, that completely depends on how representative your sample is of the population that you're trying to make inferences for.
All right. How do missing values impact the LTA matrix?
So let's talk about missing data first on the indicators. So for example, let's talk about a model at a single time with some spot missingness on your indicators. Because all of these models are fit using maximum likelihood, and maximum likelihood is a modern approach to missing data that operates under the assumption that the data are missing at random. If you have spot missingness on the indicators, those missing values are handled within the maximum likelihood procedure. And what you should do is you should include anybody in your analysis who provides at least one response to any item in your survey. Now, once we extend that longitudinally, not only do we have spot missing, we might also have attrition, probably do have attrition. Again, using that maximum likelihood estimation, it is, of course, assuming that the data are missing at random. If you have data that are missing not at random, that's a different issue, and we have to talk about that separately. But the recommendation would be that you include everybody that provides a response to any indicator at any time. So, you know, if people only appear at wave 1, that's fine. If people, if you're using later waves and you went back and you followed up with some people and all of a sudden they appear at time 3, you should put them in the analysis. Now, that response that I just gave is complicated by if you have missing data on the covariates, okay? Some software programs, well, so unless you do something special, if a person has some indicators, but they're missing the covariate or the grouping variable, those people get dropped out of the analysis in a list-wise deletion way. And so you have to be sure, you have to be careful that you don't do all of your model selection and then add in a bunch of covariates and it totally changes your sample. Some software programs, for example, M+ has an option to handle missing data on covariates by adding some lines of code focused on the variance of those predictors. And by doing that in the code, it inserts those variables into the maximum likelihood procedure and treats them as missing at random and will let you fit all of that together. People often want to know if they can do multiple imputation on their covariates. Although that is technically possible, it can be quite difficult because you have to run through the models so many times, and it's not really something that I would recommend somebody kind of start off doing. I'm not sure if that's sufficient. If people have extra questions about missing data, let me know.
Okay. A question that's come up several times. Well, I'm going to ask these in succession. In LTA, is the number of classes and items response probabilities determined using the data from time 1 or data from all time points?
I'm sorry, could you ask it one more time?
Yeah. Is the number of classes and the item response probabilities determined using data from time 1 or data from all the time points?
Yeah, okay, I'm sorry. So, yes. So if you, in the latent transition model, when you fit that model, you fit it all of the times together simultaneously. And so that model, when you look at the item response probabilities and the prevalences, that is all simultaneously estimated as one model. So information from indicators at all of the times inform that measurement model. Now, having said that, we talked a little bit about invariance across groups, right? One critical piece of an LTA is measurement invariance across time. You often impose that so the classes are, the structure of the classes are the same so that you can interpret the classes the same across time. If you can't interpret the classes the same, then it weakens your interpretation of your transition parameters. So all of that information across all of the times is used in the estimation of the model, but you might have put restrictions on the model like measurement and variance across time to make the model do something in particular, okay? Now, I think a piece that question is getting at is how do you do model selection? Do you do model selection at each time individually, or you do model selection across the whole LTA? There are different opinions about what you should do. I think the most common approach today is that you conduct model selection at each time individually to make sure that you understand what classes best represent that latent construct at each time. And then once you've narrowed in approximately the number of classes, then you fit the latent transition model and you conduct model selection again to make sure that that model fits well. You do that partially to make sure that you have enough classes, because again, in the LTA with the repeated measures, it strengthens your measurement model, and you might be able to, if you're on the border between 4 and 5 classes, you might have enough power to really identify those 5 classes. So model selection is kind of a 2-phased process with LTA. I think that's the most popular approach right now. But in terms of the actual model estimation, in LTA, it's all estimated simultaneously, and all that information goes into the parameter estimates.
When you were going through slides 42 through 45, the question came in, how do you specify different types of transition matrices in PROC LTA?
Okay, so this is a SAS-specific question about PROC LTA. This is entirely software dependent, so it's different software packages. But in PROC LTA, if you want to use parameter restrictions, and there are examples of this in the user's guide actually, what you have to do is you have to create a SAS data set that specifies all of the parameters in a particular structure, and you put in what we call the parameter restrictions. And so you specify every single one as either being freely estimated or constrained in some way. And then you have to make a second data set that has starting values for that data set. So in order to specify those transition matrices the way that I had them in the slides, what you have to do is in the restrictions matrix, the transition probabilities, the ones that are freely estimated, they're labeled freely estimated using a particular code. It's a 1. And then in the ones that you want to restrict to 0, you put in a 0 to indicate that they're restricted. And then in the starting values file, you restrict them to the value 0. So in SAS, it's an advanced, it's not for a beginner user, I guess is what I'm trying to say. So you make 2 SAS data sets, one for restrictions, one for starting values, and then you read those into Proc LTA, and it fits a model where those parameters are restricted in the way that you specify. It's actually, I'll just say one more thing. It's actually very similar in other pieces of software, although the coding is slightly different. The idea is the same. You have to write a piece of code that says this parameter is restricted to this value, and then it runs that model, and you get likelihood, log likelihood for that, and then you do your testing.
Do you need to establish measurement and variance before looking at the differences in the transition probabilities between groups?
Yes. I would say definitely yes. When you do not have measurement and variance either across time or across groups, what that means is that the interpretations of your classes are different, either different at different times or different for different groups. And so you can't directly compare, let's say your grouping variable is gender, you can't directly compare a transition probability of 50% for men to a transition probability of 35% to women if in addition those classes are defined in different ways for men and women. So generally we would establish measurement and variance before making statements about differences across levels of the grouping variable.
All right. If I'm specifically interested in how transition probabilities might be different between 2 groups from time 1 to time 2, can I just specify this alone, or should I look at the other parameters as well?
That kind of depends on your philosophy. I mean, I guess what I would say is the first thing that I would do in its own set of models is establish measurement and variance across time and across groups, and do that without looking at anything about the transitions, and just establish measurement and variance. Then once measurement and variance is established, then look at significant differences in the transitions. And the reason for that, in my opinion, is because you're focusing on specific hypotheses at a particular time. If you fit like a completely unrestricted model and compare it to a model where everything is restricted, like and it's significant in terms of it not fitting well, then you don't know if it's the transitions or it's the measurement and variance or whatever. So I would do it in a step-by-step procedure. There's also, this might be a little bit beyond what we could talk about in this particular webinar, but another way to test whether there are significant differences is, so gender, for example, you could think of it as categorical, right? If we just put in men and women, or more genders than just 2. You could put that in as a grouping variable because it's categorical, but you can also put it in as a dummy coded predictor of membership in the classes and transitions. So if you want to know if there's a significant effect on a particular transition among your different gender groups, you could put it in as a covariate instead of a grouping variable, which would give you that specific significance test.
Here's a simpler question.
Okay.
Can you use continuous indicators?
Yeah. So continuous indicators, sure. So we talked about categorical indicators here, but there's nothing special necessarily about the indicators. So, when I talk about these models, just to try to keep things clear in my mind, to me, LCA refers to a categorical latent class variable with categorical indicators. A latent profile model refers to a categorical latent variable with continuous indicators. But you can put a latent class variable or a latent profile variable into quote unquote LTA. The LTA piece is really focused on that stage sequential transition piece. So the transitions between classes over time. And you have classes, whether your indicators are categorical or continuous. So you can certainly use different kinds of indicators. With continuous indicators, measurement and variance can be more difficult to establish. But sure, yeah, you could even, if you're really feeling adventurous, you can even do mixed indicator models, although
baby steps.
But yeah, maybe have a little bourbon or something before you try that.
So another question about missing this, I'm going to read it, and if you don't have anything to add based on what you said before, just let me know, but because I'm not the expert, I'm just not sure.
Yeah, sure.
I have a data set where people are in and out of the data set. Some of the people could have 2 data points and others may have 6. Does the model account for this missingness, and can you explicitly model this?
Okay, I'm going to answer that in 2 parts. So in general, yeah, if people come in and out of the data set, that's fine. You should include them whenever they have data. Now, latent transition analysis, of course, is what we might refer to as a Markov model. So it's where you are at the current time, conditional on where you were at the immediate past time. There's no explicit assumption that those time points are equally spaced, but it does assume that everybody's assessed at like the same on the same schedule. And so I'm assuming that you're not referring to something like EMA where people have, complete, ecological momentary assessment data where people have completely different assessment schedules, but more of like people coming in and out of some kind of longitudinal study. That would be totally fine. The second part of that question, though, is a little bit different. It was, can you explicitly model this? So yeah, there's been some work in, so if you're thinking of things like pattern missingness or, some other fancy way to account for non-ignorable missing data, you can certainly do that. There's been other work looking at, so right now, the models that I talked about would have coded the data like 1 for response category 1, 2 for response category 2, and then a missing value for missing data. But some people would explicitly assess missing data as an extra category on that indicator. So missing data would be coded as a 3. And then you'd have item response probabilities of reporting, say, no, yes, and missing. And so there are a variety of things that you can do with missing data if you want to explicitly measure it. If you have missing data on the covariates, maybe you want to put in an indicator for whether people are missing or not. Yeah, you can do all of those things.
Great. Okay. And a couple more questions about model selections, some specific questions. How do you determine if you need to remove items or collapse levels of items? If you have many survey questions or you have many response options to those survey questions?
Yeah, so there are a lot of different ways that you can do that. There's no one like recommended variable selection approach or anything like that. It's really based on theory and empirical distributions of the variables. So, some useful kind of heuristics might be something like, in LCA, it can be difficult to have more than about 15 or so items at a time. It kind of makes the models unwieldy. And so you might want to think about collapsing items that really provide the same amount of information. So one example in my world of substance use might be, very low rates of a laundry list of illegal substances. We would probably collapse those into some kind of like other illicit substance use indicator. So items that have really low or really, really high base rates, generally, those don't make the best indicators, and you might want to combine them with something else. Indicators that are really, really, really super highly correlated, that are basically giving you the same information, those would be good ones to think about collapsing. If you need to decide how many response categories to use, often you need to look at the distribution of your item ahead of time, and you need to figure out if not all of the categories are being used, probably you need to collapse that in some way because there's so much sparseness in that item that it's not going to be helpful when you move into the model. I will also say that LCA models, they're not like regular regression models where you pick everything a priori, and you put them all in a model and you run the model once and you have your paper. There's often model refinement that goes on over time, and it can take, you know, a fair amount of time to refine the model and get the coding the way that you want it to be most helpful. If you have a strong a priori theory about what you're expecting, you know, then you should go ahead straight with that. Some lessons learned, I think, two in particular, I'll mention. One is, you know, if you have something, an item that's measured on something vaguely continuous, so I'm thinking like, you know, a 5 or 7 point Likert item, I completely understand why people are really hesitant to lose information on their items. I totally get it. But in my practical experience, you know, people really want to turn those into 3-level indicators, high, medium, and low. And at the end of the day, the way those models are often interpreted to make sense of them is high versus low. And so I often encourage people, if you want to have 3-level indicators, by all means, give it a try. But oftentimes people find collapsing it into binary items to be more interpretable. That is not universally true or anything. I'm just giving you a couple pointers of how to get started. Another thing that I've seen recently that seems to be becoming more of an issue is that the more and more and more indicators that you put in a model, the more and more and more response patterns that you have. So let's say that you have 13 binary items, right? You have 2 to the 13 possible ways that people could answer that pattern of items, not even including missing data. And so what will happen is if you have tons and tons and tons of items, there's so much heterogeneity in those response patterns that you can't get any signal through the noise. You can't get really clear latent classes because everybody just has a unique response pattern. And so that depends a bit on your sample size and things like that. Again, all of the models take some refinement, and there's not one clear-cut way to choose. Oh, I will say one more thing. It also depends a bit on what your research question is. So 2 sort of broad stroke approaches is that I have this set of items, and I want to see the classes that emerge from this set of items. If that's the case, then, you know, if you have one item that isn't really doing a good job distinguishing the classes, maybe you don't drop that item because you're interested in that set of items. But if it's more like you think you have these classes and you want to try to do a really good job measuring them, then in that case, maybe you drop poorly performing items that are not helping you distinguish those classes. So it depends a lot on the performance and the theory and the empirical distributions of the variables.
Yeah. Couldn't it be that I find a different number of classes in time 2 than in time 1? For example, what if the non-daters disappeared in time 2?
Mm-hmm. Yep, you certainly could find that. There are different strategies to handle that. If your measurement is strong, what can happen, so let's say that you find at time 1, let's say you have 5 classes, and at time 2 you have 4 classes. And when you fit the time 1 model, you look at all these classes and you say, okay, I really understand what they are. And then at time 2 you get these 4 and you say, okay, I really understand what these are. And oh, look, these 4 over here match these 4 really well. Then maybe what you want to do is you want to try fitting a 5-class LTA, and you impose measurement invariance. And often what will happen is it will identify these 5 classes right here at time 1, but at time 2, that missing class, it has a very, 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 very small prevalence, like 0 essentially. And so what that buys you is a really nice LTA model with measurement invariance where you can make nice comparisons, and it does exactly what you would expect. This class is just basically non-existent with a prevalence rate of 0. Sometimes you don't get that lucky, and you have to actually fit a model with 5 and with 4, and then you have to decide, are you going to do partial measurement invariance where these 4 are restricted to match, and then this one's allowed to be whatever it is. So there are different I'll call them workarounds to actually get the model to fit it, to get the model to fit the way that you want. But it's all about understanding the interpretation of the classes. Now, there's no rule that says the classes have to be exactly the same. Okay, you can fit a model where they're totally different. One good example of that might be, let's say you're studying the long-term development of deviant behavior or delinquency, right? We know that the measures of delinquency in childhood are not the same measures of delinquency that we use in, say, adolescence or adulthood, right? Those constructs fundamentally change their definition over time, and we would never expect them to be the same. That does not mean that you can't do LTA. What that means is when you interpret the transitions, you have to interpret them in the context of the fact that the wave during childhood, those classes have this interpretation, and the wave during adolescence, these latent classes have this different interpretation. Try not to name the classes the same way. That would be my advice, because then that just adds to the confusion. But there's no rule that says you can't do it. You just have to interpret it all in the context of the way you are restricting and fitting the model.
Thank you. How do analysts generally think about the effects of attrition on LTA estimates for statuses and transitions? We've spoken about missing this a little bit, but.
Yeah, I mean, there's, so again, there's nothing special. It's all the same maximum likelihood, things that you would think about in structural equation modeling and all that kind of stuff. And so the assumption is that the estimates of the prevalences and the transitions are unbiased under the assumption that the data are missing at random. And so that requires that you include everybody in the analysis anytime they appear, even if that's only on a single item at time one, for example. It strengthens that missing at random assumption. If that assumption is not met, then the estimates are not guaranteed to be unbiased, just as in any other analysis. So I'm not quite sure what else to say. There's nothing really special about the transitions compared to the other parameters.
Okay. Oh, we already answered that one, pardon me. And okay. Another sample size requirement question. This one specifically asks, are there cell size considerations when looking at transitions? What would be too small?
So I'm going to infer a little bit what you're trying to ask. And so if I don't get it right on the money, just ask a follow-up question. So I think, sample size issues about the sizes of classes and sizes of transitions, those can impact your model in a variety of different ways. There are two common things that we think about. The first one is like sparseness in responses, where the fit information, particularly the G-squared likelihood ratio test, is not a good test for model fit when you have sparseness in the observed contingency table, just like any other categorical data method. So we won't talk about that one. I think the question that you're asking is, what if you have a really, really small transition? Can you predict that transition? And the answer is, if you have really small transitions, just like in any other categorical data analysis model, that logistic regression model could fail. And the reason for that is because let's say that not very many people transition from non-daters to multi-partner exposed. Okay, so not very many people, let's say like 1 or 2%. And let's say that everybody who makes that transition used alcohol, right? That is a very strong association between alcohol use and that transition. So you know that association is strong, but just like any other logistic regression model, you can't actually fit that logistic regression model because you don't have anybody, you have a division by zero problem. You don't have anybody who was a non-alcohol user who made that transition, and so the estimate blows up. So, how small is too small to predict prevalence rates or transitions? Honestly, you kind of just have to try it. If you use a software package that does not auto-fix parameters, so that's something like if you're using SAS, for example, you can use data-driven priors to pull estimates slightly off the boundary to prevent that from happening. It doesn't really affect the parameter estimates, but it helps with that problem. But sometimes you'll just get estimates that are too small and you have to skip them in the estimation. In other software packages, M+ is a package that does auto-fixing, and so you'll get these warnings that they auto-fix certain parameters to 0 to prevent failure of the model. And so what you need to do is you need to look at all those parameters and compare it to your baseline model and make sure that the ones that they're auto-fixing match the, for example, transitions that you think are super small. So if you have a transition probability of 0, you can't really predict that. And so either it will be auto-fixed or you will have to fix that parameter or skip it in some way in the estimation.
Another, getting back to the idea of changes in the actual classes, this one goes a little further.
Sure.
What if the underlying structure of the construct you are interested changes over time? Are the classes and item response probabilities necessarily the same at each time point?
Oh, definitely not. So, I mean, as I said, there's no hard and fast rule. So LTA is framed in the literature in a very specific way. It's that they're the same latent classes assessed with the same indicators and the same response categories over time, and that they maintain their interpretation, and that you're just looking at people transitioning in and out. Okay, that's how the setup of LTA is in the literature historically. However, there's no rule that says that's the only kind of model that you can fit. All we're doing is we're taking latent class membership at time 1, however that's assessed, and predicting latent class membership at time 2, however that's assessed. So although you could not fit those models in SAS, because SAS is a very specific, PROC-LTA is a very specific program to fit one very specific model, you could use a much more flexible piece of software like Latent Gold or M+ that would let you use, for example, different indicators with different response categories at different times. And so you have a latent class variable at time 1 with a particular interpretation. You have a latent class variable at time 2 with a completely different interpretation. And all you do is you use regression to predict, you predict time 2 from time 1. And so it's that arrow. And what you're interested then, again, it's just all about the interpretation of the classes. So it's where you are in this second latent class, conditional on where you were in this first latent class. In fact, it doesn't even have to be over time, right? We're talking about these as longitudinal models, but you could have 2 totally different constructs and you just want to relate them together. If you want the word, the language that is often used for those models is something like log linear modeling with latent variables. So latent transition analysis is a log linear model with latent variables. So they're the same thing. It's just we talk about them in a particular way.
Are we able to apply survey weights to LTA?
Yes. So survey weights can be applied to LTA, but it depends on the software package that you're using. So PROC-LTA and SAS does not accommodate survey weighting. So again, you'd need to use a more flexible package. But Latent Gold, M+, other packages allow you to use survey weights. So yeah, there's no theoretical restriction on that.
Has LTA been applied to EMA or daily diary data?
It has, in some ways. I can't think of a paper off the top of my head that I could direct you to, but there are people here at Penn State who are playing with the idea of how to apply LTA to EMA. There are 2 primary difficulties with EMA data. One has to do with the data structure for EMA. If it's true ecological momentary assessment with random prompts throughout the day across your participants, there's no way to structure that data so that across the full sample, it's like a time to time to time to time transition, because time is continuous. And there are continuous time Markov models. Okay, I will say that. People are, I think, moving in the direction of applying continuous time Markov models to EMA-like data. But like a straight up LTA has not, just kind of been imported into EMA because of this time spacing issue. The other issue is that if you can imagine having many times, those transition matrices can be overwhelming to interpret. So even if you had like the NLSY 97 data, which is that dating and sexual risk behavior, they have like 20 waves of data now. So you would have 19 transition matrices that you're trying to explain. But you might be interested in something like stationarity, like are all of the transition matrices the same? So, LTA is, it can be, if you have many times, it comes down to more of an interpretation problem than anything. And so EMA is highly intensive. And so it kind of depends on how the data are structured and how many transition matrices exactly you want to interpret. You might be better off using something more like a continuous time Markov process. The issue there is that those are, they don't account for measurement error necessarily. So that's a great question, but it's not a straightforward answer at this time.
Yeah, jumping around a little bit because I have a related question.
Sure.
It seems that this technique is good for cohort studies or longitudinal studies with limited waves of data collection. Do you recommend the LTA technique for diary studies? What, in your opinion, is the maximum number of waves? I think that's Felicia's question, by the way.
Yeah, I think that there are a lot of unique ways that you could apply LTA to EMA data. But you need to think through the intents issue. When you apply LTA to panel data, I've done it up to 7 waves, which is kind of reasonable, I guess. But if you don't have stationarity, you have to put 6 transition matrices in your paper, and you have to interpret all of those parameters. So, even in more straightforward EMA approaches, like, multi-level modeling is a fairly common approach. It does a great job at measuring all of the different assessments, but it really summarizes them in some small set of parameter estimates. LTA has a massive number of parameter estimates, and the more times that you add, it just, can become unwieldy. So I don't have a straightforward answer to that, but hopefully you guys kind of get the flavor of it.
So does LCA or LTA assume a normal distribution of the construct in the population or sample?
It assumes a multinomial distribution of the latent construct. Again, it's categorical. Now, it depends. For those of you who are maybe not so interested in the math behind it, you can tune out for a couple seconds. There are really two primary ways that you can parameterize the model. One is more based on what we talked about here, which is where you straight up use the multinomial distribution on the latent class variable, and you assume not a normal distribution, but the multinomial distribution on the classes. However, you can also reparameterize the model to estimate it where the underlying latent variable is continuous, and you identify thresholds that match, basically thresholds from moving from one class into another. So for example, M+ estimates their models that way. So they assume an underlying continuous distribution with these thresholds that separate the latent classes. It turns into, at the end of the day, the same model. So it kind of depends. Theoretically, what you're interested in is a categorical latent variable as opposed to a continuous latent factor. but you can parameterize the model such that it is an underlying continuous variable for purposes of estimation.
Right, thanks. Can latent class modeling in general be used to identify poor indicators or poor class separation?
Yeah, Linda Collins would love that question, so congrats to whoever asked that question. Yes, you can. So actually, latent class models historically came from more of a measure development world. It's not really used that often today. It's used much more exploratorily today. But if you had a strong theory about a construct and you wanted to make a measure to assess classes, like you think that there are these different classes out there that you want to uncover and you want to create a high quality measure, you would ask questions, you would fit the latent class model in a bit more of a confirmatory way with the classes that you think exist, and you would drop items that are not performing well at identifying those theoretical classes. And you would do that by considering things particularly like homogeneity. So again, you want estimates that are close to 0 and 1 because you want to identify those classes in a really strong way. You might also drop indicators that are not helping separate those unique theoretical classes. So yeah, you could certainly do that. One thing that I think can be a little bit tricky, and this is also tricky in factor analysis, is this sort of iterative procedure that people want to do where they don't have a strong theory and they don't know the measure, and so they fit it and they identify what the classes can be, and then they drop items, and then they refit it and see what the new classes are, and then they drop some more items. I think you have to be careful about an iterative procedure where you don't have a clear idea on either of those two domains. But if one of those is clear, you either really want the items and you want to know the classes, or you know you have theory for the classes and you want to develop a good measure. When one of those is really strong, you can certainly, you can certainly drop items based on that.
All right. I'm sorry, I'm not sure I understand this question. Do you need to replicate your LCA on a subsample or different time before moving to an LTA?
Yeah. Okay, so I'm going to unpack that question. I think I'm going to answer the question I think you're asking. So I'm going to answer two different questions, actually. So let's say that you have just a single time, right? The question you could ask is, do you need to do some kind of replication or cross-validation or something like that? That entirely depends on how large your sample is. A lot of people like to do, like a sort of cross-validation procedure where they take part of their sample and they do like an exploratory LCA, and then they run a model with that many classes in the confirmatory piece to kind of replicate, make sure that they have the right class model. You could also do some kind of model selection in multiple subgroups of the sample and then combine them together, something like that. So yeah, you could certainly do all of those things. The question about moving to LTA, I think the thing I want to say about that is that kind of speaks to this idea that I said most people are using for model selection today, where they really do model selection at each time to make sure they understand the classes that well represent that time. And so that's a bit like a replication, and then you would do that before you would put them all together into the overall LTA. If that doesn't answer your question, maybe you could ask a follow-up.
All right. In LTA, so we've talked about missing data, but would you include a participant who only had data at time 1 but not at other time points?
Yes. Easy. Again, anybody who has any information on any indicator at any time strengthens the missing at random assumption, and you should include them. So if the only question I answered is, did you use substance use in your lifetime at time 1? If that's the only question I answered, I am in the sample.
Are you able to evaluate statistical significance of specific odds ratios or regression coefficients when you are looking at covariates in LTA? Or are you only able to know if overall the covariate is associated with the transitions?
No, you can look at specific odds ratios. What is exactly presented in the output depends on the software package. So in Proc LTA, we don't have standard errors. So you can't like compute confidence intervals or anything. In more flexible pieces of software like Latent Gold and M+, they do not print out an overall omnibus test, but they do print out the individual effects. And so you get an estimate of standard error and a walled statistic for its significance. And then if you use a little confidence interval command, it'll give you a confidence interval too.
What if your attrition is not missing at random?
If your attrition, so just to be clear, right, missing at random means that the data can be dependent on things that are in the model. Missing completely at random means that it's just completely at random. So almost every analysis these days assumes that things are missing at random. If you really, and the goal usually, but not always, is to strengthen that missing at random assumption. If you really truly believe you have non-ignorable missing data, so that means missing data that are missing not at random, you have to use an MNAR approach. And there are any number of papers in the missing data literature about, a million different ways. Pattern missingness would be one way that's been recommended with LCA. You could try to model the distribution. But if you have data that are missing not at random, you have to use a missing not at random approach that's been proposed and overlay that onto LCA. There's no, but that's true for any model.
What do you do if your time points are not equally spaced?
So if your time points are not equally spaced, there's nothing special that you have to do when you fit the model, because again, the traditional LTA is just a Markov process, and so it regresses time 2 on time 1, regresses time 3 on time 2, and so on. It doesn't make the assumption that those times are equally spaced. It just does the regression that you specify. And so what you have to do is you have to interpret those transition parameters in the context of the spacing for that particular transition matrix. So for example, if you have 1 year between time points and then you have 2 years between time points and your transition parameters are different, like maybe one transition parameter is 50% from time 1 to time 2, and then it's like 70% from time 2 to time 3, that could simply be the additional extra year that you gave people to transition. But there's nothing special you have to do in fitting the model. It's all in the interpretation.
All right. One concern I have heard raised is that with LCA, LTA, the analysis will always find classes. Are there ways to ensure that the classes are not spurious, or is that more of an interpretation and theory issue?
Yeah, so I have a couple different things to say about that. Spurious classes, another way to say that is like how generalizable is that model and how replicable is that model? I mean, it's that, you could get around questions like that by using, if your data are big enough, doing some kind of cross-validation procedure. That concern, in my opinion, is raised a lot more frequently in LCA than it is in factor analysis, but the problem is exactly the same in factor analysis. Factor structures are not exactly replicated either. The factor loadings are often not the same from study to study, but people don't seem to have nearly the problem with it there. So what you want to do is you want to make sure that you don't tailor your latent class model too closely to the sample. And things like the AIC and BIC and other tools, that's going to help you balance the fit and parsimony. So you don't want to over extract. The other thing I will say about that is I think the real criticism that people have about that is what I think of as sample telescoping. So if you have a sample size of like 10,000 people and you're asking about substance use, right? And you ask them, have you ever done this? with the power and the way these models work, depending on the strength of your measurement, you know, maybe you're going to identify 5 or 6 or 7 classes, okay? But now let's say we take that sample of 10,000 and I look at only the people who've reported substance use in the past year, okay? Well, again, you're probably going to find, you know, 5 or 6 or 7 classes. And then let's say you look at only the people who had problematic use in the past month. Again, you might find 5 or 6 or 7 classes. Why is that? That's because the power changes in those samples, right? Like you're looking at slightly different things, and the models are always going to have power to roughly detect about the same number of classes. So this is the criticism that I've heard, but it's a power issue, like how much signal within the noise can you detect? And in the overall sample of 10,000 people, you probably have a huge group of people who are either non-users or light users, right? And as soon as you remove that huge class, you change the power to telescope in to the more specific sample. And so now you can get more specific classes among that smaller sample. And so that kind of happens as you telescope down. That's one thing people don't like. Although, honestly, that's not that much different than other regression models where, you know, if you have a huge group of non-users as your predictor, you can't find effects of like a super small level of problematic use. Anyway, the other thing that I will say about that is the other criticism that I think is really valid, and it's often leveled at latent class models, is that you always identify these classes that are like low, medium, and high, or low, low, medium, and high, or something. To me, that type of thing happens in applications that are not particularly well suited to LCA. The hallmark of LCA is really this multi-dimensional nature. And if you put in something that's basically unidimensional, it's going to artificially chop it into this low, low, kind of low, medium, kind of high, and high, high, right? And so if you don't apply LCA, I mean, if your research question or your measures are not well applied, you're going to get classes that that are not, they're not good applications of the method. Like there would be something better that you could do that treats it more continuously instead of artificially chopping it up. You know, I think historically there's been, you know, a fair number of papers that have published like low, medium, and high classes. And so that's kind of where that criticism has come from. I think if you really truly use LCA in the multidimensional way that it is a best fit for, I think that you will not see those, you won't see that happen as often. But that's my personal opinion. Hopefully that helps.
All right.
Respond to a reviewer.
we are out of time, and we have a few questions we haven't gotten to yet.
Sure.
But there are 2 left that we really haven't touched on.
Sure.
Can I ask those briefly? And so I have indicators that are consistent across 3 waves of data, but in the 4th wave, additional indicators are included. Can I include these new indicators in the analysis, or do indicators have to be exact across all time points?
Well, again, there's no hard and fast rule that says everything has to be exactly the same. You can certainly fit in a software program a model that has additional indicators at wave 4. You can physically fit that model. I think the things that you need to think about, though, is that at that last wave, that latent class model is going to try to summarize classes across a different set of information than your first 3 times. And so you might get different classes, where if you just used the indicators that did match, you might have a much more straightforward interpretation. So I guess my answer to that and all of those similar kinds of questions is that, yes, you can fit that model. And it's really all about, are the classes the same? Can you interpret it? The other thing I will say, though, about that is if for whatever reason you really, really, really want to do that, you can think about partial measurement invariance, where the measurement is invariant across the 3 times, and then it's invariant across the consistent indicators at wave 4, and then the additional indicators are allowed to have their own measurement. But again, because you're summarizing a different set of information, your classes are probably going to be, different. And I think in the case that you're describing of 4 times, that is going to be hard to explain to the reviewers of a paper.
So this is the last question I'm going to ask. Mm-hmm. If, the questions are coming in 2 different modes, if I missed any and didn't realize it, please send an email to mchelpdesk@psu.edu, and we'll try and get you a response in the next couple days. The last one I'm going to ask for today is it possible to use LTA to have one set of profiles predict another set of profiles of different constructs at the same time point? For example, could you use LTA to have profiles of drug use predict profiles of sexual conduct?
Yes, you can. So again, there's nothing special. I think I kind of answered this earlier when I said it doesn't even have to be time 1 and time 2. It could be 2 different things at a certain time. Again, all of these models that we're talking about fall under this very large umbrella of log linear modeling of latent variables. Would you technically call a model that is using substance use to predict sexual behavior an LTA? No, I wouldn't probably use that exact phrase, because LTA was designed for one very specific application. But what you could say is you could say something like an approach conceptually similar to LTA. You could say that. You could say log linear modeling with latent variables, and you could reference work by Jacques Hagenaar. Whoever asked that question, I would strongly encourage you to look at a paper. It's a Bray, Fody, Thompson, and Wills. I think it's in Leadership Quarterly, maybe in 2014 or 15. That paper is in the context of IO psychology, but it does exactly what you're describing. It just conditions, what you're talking about doing is conditioning latent class variables on other latent class variables. I call that log linear modeling because log linear models are designed for categorical variables. Other people would just call that categorical structural equation modeling. So yes, you can certainly do that. It's just regressing one latent class variable on another. Mm-hmm. So you look at that paper. Another paper you might be interested in is Bray, Lanza, and Collins 2010 in structural equation modeling. Actually does actually what you said. So there's it uses this dating and sexual risk-taking latent transition model, and it predicts that latent transition model from a latent transition model of substance use. And so you can see how flexible these models are. It's just linking them together in like a large structural equation modeling framework or a large log linear modeling with latent variables framework. Yeah. Great questions, advanced questions. This is great.
Yeah. All right, Bethany, thank you very much for this today, and thanks to all of you who stuck around to the end of the Q&A.
Yeah, thank you so much. Have a great weekend, everybody.